Hi everyone, I'm Miaoyun and I'm from Nanjing University, and for some reason we have to present our paper through this video. We apologize for the inconvenience, and if you have any questions, please feel free to send an email to us. First, I will briefly introduce code summarization. Basically, code summarization is the task of automatically generating succinct natural language summaries for given code snippets, and it has been a hot search topic in software engineering. Code comments are vital for enhancing program comprehension and facilitating software maintenance, but writing comments is often labor-intensive and time-consuming, so high-quality comments are often absent, mismatched, or outdated during software evolution. Therefore, automatically generating code summaries can improve the comprehensibility and maintainability of software. And that's the background of source code summarization. Next, let me introduce the application of large language models in code summarization. This figure shows the general workflow, which consists of summary generation and summary evaluation. In the summary generation process, the input consists of a code snippet and the expected summary category. The taxonomy of code comments, which is proposed in previous research, classifies comments into 6 intent-based categories that correspond to descriptions of the code's functionality, design rationale, implementation details, inherent properties, usage instructions, and others. So the input is passed into a prompt generator equipped with various prompt engineering techniques, and the prompt generator will construct a prompt based on the input. This prompt is used to instruct large language models to generate a summary of the expected category for the code snippet. And in the summary evaluation process, a common practice is to compute the text or semantic similarity between the summaries. And there have been several studies investigating the effectiveness of large language models in code summarization, but they still have some limitations. First, most of them only focus on one prompting technique, while some advanced prompting techniques have not been investigated, like chain of thought. And second, they overlook the impact of the model parameter settings. There is no empirical evidence showing that large language models remain well in all model settings. And last, these studies evaluate model performance using text similarity or semantic similarity, but these metrics have critical limitations. Here is an example. The comment generated by StarChat gets higher scores in text similarity and semantic similarity, but as we can see, the comment generated by GPT-4 has greater clarity and contains more information. However, its description is different from the reference comments, like it uses release instead of unlock, and it contains more details that do not exist in reference summary, so it gets lower score. This is not in line with human perception. So motivated by recent research in large language model-based evaluation, we also use large language models to evaluate code comments. In this case, GPT-4 achieves a score of 5, while StarChat only gets a score of 2. So in conclusion, there are some shortcomings in existing studies, and to address these issues, we conduct a systematic study on code summarization in the area of large language models. In RQ1, we systematically investigate what evaluation methods are suitable for assessing the quality of summaries generated by large language models. And in RQ2, we aim to reveal the effectiveness of several popular prompting techniques like few-shot and chain of thought. In RQ3, we adjust the parameter settings to control randomness of the LLM's output and see the impact of them on code summarization. In RQ4, we study LLM's capabilities to summarize code snippets across diverse programming languages. And in the last RQ, which is RQ5, we aim to explore LLM's ability to generate different categories of summaries. Next, I will introduce our experimental setup briefly. The models we use in the experiment are 4 representative LLMs. Code Llama and StarChat as representative code large language models, and GPT-3.5 and GPT-4 as representative general large language models. And we investigate 5 prompting techniques, which are zero shot, few shot, chain of thought, critic, and expert. Due to time constraints, I will not introduce them one by one. Please refer to our paper for details. For programming languages, we choose the 6 programming languages in CodeSearchNet and C in ICSE2025. Besides, we built the dataset for Erlang, Haskell, and Prolog ourselves, following the steps of constructing CodeSearchNet. In RQ1 to RQ3, we only experiment on 3 popular programming languages, Java, Python, and C. In RQ4, all the 10 programming languages are investigated, and in RQ5, we only experiment on Java. So let me introduce the results and findings of RQ1, where we want to find out the most appropriate evaluation methods as alternatives for human evaluation. We consider 4 types of evaluation methods. The first type is methods based on summary-to-summary text similarity, like Blue, Meteor, and Rock. And the second type are methods based on summary-to-summary semantic similarity, including BERT score, sentence BERT with cosine similarity, sentence BERT with Euclidean distance, and the universal sentence encoder with cosine similarity. The third category is methods based on summary-to-code semantic similarity, such as SIDE. And inspired by recent work in natural language processing, we also investigate the feasibility of employing large language models as evaluators. We randomly select 50 samples from Java, Python, and C datasets and employ few-shot prompting to generate summaries using the 4 large language models. First, we conduct human evaluations. And Table 2 shows the results. We can observe that the quality of reference summaries in existing datasets is not particularly high, and summaries from general-purpose large language models are better than those from specialized code large language models. Then we compare the correlation between automatic evaluation methods and human evaluation. Table 3 displays the scores of automatic evaluation methods and large language model-based evaluation methods. Observe that overall, methods based on summary-to-summary semantic similarity tend to give higher scores to specialized code large language models, and SIDE tends to give higher scores to StarChat, while large language models-based evaluators tend to give higher scores to general-purpose large language models, which is the same as human evaluation. Also, we can observe that LLM evaluators assign low scores to reference summaries. It means that similar to human evaluation, LLM-based evaluation methods also believe that the quality of the reference summaries is not very high. And based on above observations, we can reasonably speculate that compared to traditional evaluation methods, LLM-based evaluation methods may be more consistent with human evaluation. Therefore, we calculate Spearman's correlation coefficient and the p-value between the results of different evaluation methods and human evaluation. The results demonstrate that GPT-4-based method overall has the strongest correlation with human evaluation. For more details, please see our paper. So, in subsequent RQs, we use GPT-4 as the evaluator. It will assign a score from 1 to 5 to each generated summary, with a higher score representing higher comment quality. And in RQ2, we compare 5 different prompting techniques. We randomly select 200 samples each from Java, Python, and C datasets. And the result shows that in practice, selecting the appropriate prompting technique requires considering the base LLM and the programming language. Next, in RQ3, we investigate the influence of model parameters, top P and temperature, that control the randomness of large language models' output. Due to time limits, I will directly introduce our findings, and for more details, you can refer to our paper. So we observe that, first of all, the impact of top P and temperature is small, and it is specific to the basic LLM and programming language that like whether higher randomness or lower randomness will be better. And as alternative parameters, top P and temperature have similar influence on the quality of generated summaries. And in RQ4, we conduct experiments on 10 programming languages, which can be classified into 5 types. It is observed that GPT-4 surpasses all other 3 models on all 5 types of programming languages, but the program language of the code will affect the quality of the generated summaries. For procedural programming language, LLMs overall perform better on Go than on C, and for scripting programming languages, all 4 LLMs perform better on PHP than on Python. For functional programming languages, specialized code LLMs perform better than Haskell than on Erlang, whereas the reverse is true for general-purpose LLMs. And all the 4 LLMs perform worse in summarizing logic programming languages than in other languages. And in the last RQ, we investigate LLM's performance in generating different categories of summaries. Following existing studies, we classify code summaries into the following 6 categories according to their intents, and we employ the common classifier coin provided by previous researchers to classify the CodeSearchNet Java dataset into 6 subdatasets according to the common intention type, and randomly selected 180 samples from each subdataset. And the results show that the 4 LLMs excel in generating different categories of summaries. Like the smallest code llama outperforms GPT-4 in generating Y and property summaries, and StarChat is not proficient at generating how-to-use summaries. And GPT-3.5 and GPT-4 perform worse in generating property summaries than other categories of summaries. So in conclusion, we provide a comprehensive study covering multiple aspects of code summarization in the era of large language models. Our interesting and significant findings are as follows. First, compared with existing automatic evaluation methods, the GPT-4-based evaluation method is more fitting for assessing the quality of large language model-generated summaries. And second, the advanced prompting techniques anticipated to yield superior performance may not invariably surpass the efficacy of straightforward zero-shot prompting. And the third, the 2 alternative model settings, temperature and top P, have a similar impact on the quality of LLM-generated summaries, and this impact is small and varies by the base LLM and programming language. And LLMs exhibit inferior performance in summarizing code snippets of logic programming languages. And the last, Code Llama with 7B parameters demonstrates superior performance over the advanced GPT-4 in generating Y and property summaries. Our comprehensive research findings will aid subsequent researchers in swiftly grasping the various aspects of LLM-based code summarization, thereby promoting the development of this field, and the code and data and the experimental results can be found in our GitHub repository. That's all for my presentation, and again, sincerely apologize for not being at present. And if you have any questions, please send emails to the following address. Thank you for your time and attention.